So here we're going to continue with our rotor stator example. In a previous video, we set up the problem and we solved part A, where we found the water velocity coming out of the stator of our stator-rotor turbine combination. In this one, we're going to look at the design of the rotor, and specifically, we're going to find the inlet and outlet angles of the rotor such that the water enters the rotor parallel to the leading edge of the blade, and in part C, at the outlet, the water will be exiting so that it has no tangential velocity in the lab reference frame, in the stationary reference frame. And then we're going to calculate the power produced by the rotor. So in part A, we went and analyzed the flow through the stator, which deflects the flow by 10 degrees in the circumferential direction. And we found, most importantly, that the radial velocity of the flow was 9.947 meters per second, and the tangential velocity was 1.754 meters per second. So, since we drew our rotor in red on the other page, I'll switch to the red pen here. I'll try to. Yes. And let's look at our rotor. It has an inner diameter of 0.8 meters and an outer diameter, radius, not diameter, an outer radius of, I believe, let me check, 1.5 meters. And it is rotating in this direction at a speed of 120 RPM. Now, to figure out the angle that we want these blades to be at, we have to consider the fact that in the stationary reference frame of the stator, and I'm going to draw a larger picture over here on the right. So if you remember, our stator curved the flow like this so that it came off at a 10-degree angle. And now our rotor is going to come by, and it's going to have the blade that looks something like this because it's moving to the left in our picture at some speed. And so the water velocity from the stator in the absolute frame is going to have some velocity like this that looks like v. And then, of course, our rotor is moving with some rotational velocity u. And as we remember, v is equal to u plus w, the relative velocity. And so that means that w will be something like that, right? Because v is equal to u plus w. And we want to find the angle of this blade here, and we'll call it phi1. We'll try to write a little better here. We'll call it phi1. We want to find this angle such that the blade is parallel to this relative velocity w as it's coming into the rotor. So we know, as we just said, that v is equal to u plus w. We know from above that v, the absolute velocity, is equal to 9.947 r hat plus 1.754 theta hat. That's what we found from the 10-degree turn in the stator in part A. We know that u, the velocity of our rotating reference frame, is given by omega r. I'm going to call it r1, since we're calling this phi1, the angle at the inlet. I'm going to call it r1 here, and I'll call this r2 there. And that's going to be in the theta hat direction because our, if you remember from before, our coordinate system is such that r hat points outward, of course, theta hat points in a counterclockwise direction, and then z hat comes out of the screen. So this is equal to 120 rotations per minute, and we have to multiply that by 2 pi radians per rotation, and 1 minute is 60 seconds. So that's the omega part, and then r is 0.8 meters, and when we do the math on that, we get 10.05 meters per second in the theta hat direction. Now we know that from our vector triangle up here, which I haven't drawn particularly well, but u should be straight to the left here, and so it's clear that actually u should be straight in the circumferential direction. So let me redraw those just so that we're completely clear on what's going on with our vector triangles. Let me scroll down just a bit here. So if we look, we know that V looks like this, where it's angled to the left by 10 degrees. We know that U is going straight left at some point, if this is the rotor as it's coming around. And again, we have our r hat and our theta hat unit vectors. And we know that W looks something like this, because V equals U plus W. So when we draw it a little better like this, it is hopefully clear that W, the radial component of W, has to be equal to the radial component of V. And that's because simply there's no radial component of U. So therefore, we know that WR, which is just the radial component, not a vector, just the radial component, is equal to VR, is equal to 9.947 meters per second. We know that W theta, the theta component of the relative velocity, well, that just has to be V theta minus U theta. And when we do the math on that, we know that V theta is 1.754. We subtract off 10.05, and we get minus 8.30 meters per second. So if W is going to be parallel to our blade up here, then we see that the tangent of phi1 has to be equal to minus W theta over WR. Let's be clear on why that is. If that vector is going to be parallel to the blade, then this angle here has to be, oops, not Q, but phi1. This is W theta. This is actually minus W theta. And this is WR. Sorry, this is not minus W theta. This is, of course, just W theta because that's the way I've drawn the vector. But because phi1 is drawn as it angles off to the right here as opposed to angling to the left, what we really want is the absolute value of W theta and the absolute value of WR. So I should probably write that a little more formally like this. And when we do that, we find that phi is equal to the inverse tangent of 8.30 over 9.947, which is equal to 39.84 degrees. So that's the angle that we have to have our blades so that the flow coming into the rotor is parallel to that leading edge of that blade. And now we need to do something similar at the outlet for part C. Just to refresh your memory, we'll scroll up here. Find the outlet angle phi2 such that the exiting water has no tangential velocity component in the absolute reference frame. And then we're going to calculate the shaft power produced by the rotor. So we go back down here, start a new page, and we'll draw our vector triangles again. Looking at the outlet of the blade in close-up, we're going to have something like this, where we've specified that W, the relative flow, is going to be parallel to the outlet of the blade. We've said that V is going to have no velocity in the tangential direction. That means it's going to be purely radial like that. And so because V equals W plus U, we're going to use what we know about U, the motion of our rotor, to determine what angle this is going to be here, phi2, such that V is only in the radial direction. Well, we know that V is equal to VR r hat plus 0 theta hat, and that is equal to U plus W. So that means, wait a sec. So we know about U because we know that U is equal to omega R2, the radius of the outlet of our rotor, theta hat, because the rotor is going to the left here. And when we do the math, we get, let's see, 120 RPM, rotations per minute, times 2 pi times 1 over 60 seconds per minute, times the outer radius is 1.5 meters, and that ends up being 18.85 meters per second in the counterclockwise direction. So that means that the theta component of W, which is equal to V theta minus U theta, has to be equal to 0 because V theta is 0, minus 18.85 meters per second. And so, of course, that equals minus 18.85 meters per second. Now, we also need to know what WR is so that we can find the components here, right? Because if we draw W a bit larger, we see that we have an R component and a theta component, and this angle here, phi2, will be determined when tangent phi2 equals the absolute value of W theta over WR. But just as we did in the first part of this example, we showed that the flow rate, Q, has to be equal to the outlet area times the radial component of the velocity. And I guess I should write this as VR because at the moment that's all we know is VR in the absolute frame. But we know from our vector triangle that VR and WR have to be the same thing. So this is just equal to A WR. And so therefore we can solve for WR is equal to 20 cubic meters per second over the area, which is 2 pi times 1.5 meters, which is the radius, times 0.4 meters, which is the depth of our rotor into the screen. And we find that, after some math, equals 5.31 meters per second. So therefore, the angle at the outlet is going to be equal to the inverse tangent of 18.85 over 5.31, and we go through and we do the math, and we see that that's equal to 74.3 degrees. So to recap, our rotor blades will look something like this, where this angle, phi1, is equal to 39.84, so almost 40 degrees. I'll put a little squiggly here, almost 40 degrees. And this outlet angle is quite tipped at 74.3 degrees. So phi2 is roughly 74 degrees. And when we do that, in the relative frame of the rotor, once again, the flow will come in parallel to the leading edge. We've specified that it will leave parallel to the trailing edge here, but in the stationary reference frame, it will have a purely outward component because, of course, the motion of the rotor blade to the left will exactly counter the theta component of the relative velocity to the right. We can calculate the torque, again, from the conservation of angular momentum, and that's going to be the integral over the control surface of rho times v cross, r crossed v times v dotted with n hat, integrated over the area. And we're going to have both an inlet and an outlet as our control surfaces. But we just said that the absolute velocity of the exit of our rotor is going to be purely radial. And so when we do r crossed with v, we get r cross r hat cross r hat, and that is identically 0. So the outlet will contribute nothing to the angular momentum equation. So that means at the inlet, we have the integral over the inlet of rho r cross v times v dotted with n hat dA, which is going to be equal to the integral of rho times, well, let's see, r cross v is going to be the radius at the inlet, which is 0.8 meters, times r hat, crossed with, let me back up one sec. We're going to cross r with v, which means that we're going to get r, something in the r hat, crossed with v, which has both components in the r hat and the theta hat direction. But r cross r, of course, is 0, so we only need to worry about the theta hat direction. So we get r, which is 0.8 meters, times v theta, which is at the inlet. Where is v theta? Here it is. 1.754 meters per second. And then we're going to have v dotted with n. Well, n is going to be, the outward pointing normal is going to be in the minus r hat direction, which means that we only need to worry about the vr component of that. And vr at the inlet is equal to 9.947. So here we get times minus 9.947 meters per second, integrated over dA. And when I did this cross here, I ended up with a z hat in my cross product. So now when we do the integral over the area, because we've assumed steady in the mean, we see that the flow across the boundary that's normal to the boundary integrated over the area, well, all of that is just going to give us q, in this case minus q, because we have a minus sign here. So all this is going to be equal to rho times minus q times this here, which is 0.8 meters times 1.754 meters per second, or 1,000 kilograms per cubic meter times 20 cubic meters per second times 0.8 meters times 1.754 meters per second. We got a minus out in front of this. And then when we go and do all the math, we end up with minus 28.1 kilonewtons. Sorry, not kilonewtons per meter, but this is torque, so it's kilonewton meters. And I'm going to leave the z hat in there. The minus sign means that the torque is acting in the negative theta hat direction. So it's acting in this direction here, which means that the water is actually applying torque to our rotor because we are applying negative torque to the water, if you want to think of it that way. Notice that this torque here, minus 28.1 kilonewton meters, is exactly opposite the torque on the rotor, the stator, which was 28.1 kilonewton meters. And this is hopefully apparent to you because at the inlet of, if we draw a control volume around both the stator and the rotor, we note that the water coming into the stator is coming in with no tangential component. The water leaving the rotor is coming out with no tangential component. And therefore, there is no net transfer of angular momentum around the control volume that includes both the stator and the rotor. Now, this is a little bit paradoxical because, of course, the work being done is equal to the torque dotted with the rotational velocity. And so that's going to be equal to 120 RPM times 2 pi times 1 over 60 to convert to seconds times minus 28.1 kilonewton meters, which is going to end up being minus 352.7 kilowatts, meaning that we are extracting this amount of power from the turbine. We're using the water going through the turbine to produce power, which could be used to make electricity or grind flour or whatever you want to use this particular power for. It's a little bit paradoxical because there's no net flow of angular momentum into and out of our rotor-stator combination. We showed, but yet there's still power being extracted from the system. And I'm going to leave it to you to figure out how you can show that there's power being extracted. And it's not just a matter of, well, if we divide it and we show that there's no power in the stator, that of course all the power has to come from the rotor. There's a more fundamental reason for it. And again, if you draw a control volume around both the stator and the rotor, which I've just drawn a very terrible control volume, but if we draw a control volume, here's our inlet, here's our outlet, you should be able to show where the power is coming from. And I'll give you one small hint, which is don't think about angular momentum, but think about how you would go about calculating the pressure at either the inlet or the outlet of this system.